thank you for the introduction. Hello, my name is Sven Poeggel, and today, my name is Sven. Okay, thank you for the introduction. Hello, my name is Sven Poeggel, and today I would like to show you our research in the field of optical fiber sensors. This was a collaboration between the University of Limerick and the Cyprus University of Technology. And in this research, we used a femtosecond laser to inscribe a Fibre Bragg Grating into a tip of an optical fiber pressure sensor, which is based on a Fabry Perot Interferometer. And during my presentation, I would like to guide you through 5 chapters. First of all, I want to introduce the topic, why we use FPI sensors and why we want to improve them, and then something about the theory. After this, I will explain how we inscribed the FPGs into the FPI sensor, and then some of the results. At the end, there will be a conclusion. So let's start with the introduction. Why we want to improve FPI sensors. Yeah, optical fibers comes with inherent advantages, like the small size and the low attenuation. And this is why we use the sensors for biomedical and ocean-based applications. Especially for biomedical applications, sensors have to be reliable, accurate, and stable over time. And the small size of optical fibers makes them especially interesting for volume-restricted areas, like the blood vessels or the brain. Even recently, we went to the Federico II hospital in Italy and used our sensors for measurements in vivo in several patients. Yeah, and in these measurements, we saw what we have to improve with FPI sensors. For example, if you decrease the diaphragm thickness by a factor of 2, you can increase the sensitivity by a factor of 8. But for this research, we wanted to go in a different direction. It is highly desirable to inbuild a temperature sensor into a pressure sensor for simultaneous measurement, especially for doctor and patient, since it's very convenient to use only one sensor for 2 measurements. And we thought how to inscribe an FBG. We decided to try it with a femtosecond laser. Of course, this comes with many challenges, since the process is quite complex, but we would gain many advantages, like we could select the wavelength of the grating or the reflectivity. Yeah, but before I show you how we inscribed the grating, I would like to talk a little bit about the theory of our sensors. So our sensors are only made out of glass. This means we use a single mode, a glass capillary, and a multimode. We fuse the capillary together with the multimode and push the single mode into the glass capillary, which forms a cavity and gives us the FPI spectrum. And at the end, we cut the multimode and polish it down to an ultra-thin diaphragm. On the left side, you see the schematic, and on the right side are microscopic pictures. And since we don't use any glue, there is no adhesive which absorbs water over time. So this is why we have a very good stability. We also went to the Cleveland Clinic in Ohio, which is one of the biggest medical complex, and we saw our sensors have a better stability than their medical equipment. Yeah, so with a diameter of only 200 micrometer and a resolution of 0.1 millimeter mercury, these sensors are sufficient for medical application. And for our equipment, we only use a broadband light source and an optical spectrum analyzer connected by a 3dB coupler. For our biomedical and ocean-based application, we also use an optical switch for differential pressure analysis. Since we use an optical spectrum analyzer, which acquires the spectrum from 1500 to 1600 nanometer, we can acquire the FPI and the FBG simultaneously. Here in this schematic, you see the cavity, which forms the FPI spectrum, and the FBG, which gives a sharp peak. And since we acquire both measurements together, we can split the spectrum into FPI and FBG part and use them for pressure and temperature measurement. And with this, I would like to explain how we inscribe the FBGs into the sensors. For the inscription setup, we use the same setup like in the measurement, except that we also connected a red light, and the light from the source is traveling to the tip of the fiber and indicates a successful description with a scattering of red light. We also observe it with a high-resolution camera, and we mount the optical fiber pressure sensor on a microscope sample holder, which is adjusted on a nanometer precision-controlled X and Y stage, controlled by the inscription controlling unit. And this also controls the femtosecond laser. The femtosecond laser is timed precisely to inscribe the grating into the core of the fiber, and everything is observed in real time by the camera. Yeah, for the femtosecond laser, we used a high Q laser from Femtoregion, a very expensive device, and the laser is traveling from the source over several lenses and mirrors to our X and Y stage, where it hits a dichroic mirror and focus into the core of the fiber. And here in green, everything is observed in real time. Yeah, but during our research, we encountered several problems. For example, every sensor is handmade, and as well as the adjustment on the microscope sample holder. The core of a single mode fiber is only around 8 micrometer, so a small angle has already a high impact. In recent research, there was already inscription of FBGs into the core of a fiber with a femtosecond laser, but in our case, it's a little bit more complex. In our case, we have a capillary which surrounds the single mode fiber and also captures some air, especially where the capillary is fused to the cladding of the fiber. There is an unequal distribution of glass and air mixture. And since all the sensors are protected by an oil layer and a glass plate, we have a 6-layer problem. So this means the laser, in our case, has to penetrate 5 layers before it focuses into the core. So there were many parameters we had to adjust before we were able to inscribe into the core of a fiber. But we found a solution for all the different problems, and one of the solutions are to use different techniques. 2 of the techniques I would like to show you on the next slide. The first one is the point-by-point technique. This means we inscribe an FBG alongside the core of the fiber. For this, we focus into the core of the fiber and adjust several parameters, and then we inscribe a direct line. This is a very easy and fast process, but since this process is very fast, we couldn't interfere. So we developed a sawtooth technique. A sawtooth technique is a little bit more complex. We don't write anymore in the direction of the core. We are writing the grating now perpendicular, which means we have a wider area and get the reflectivity even sooner. Also, the inscription is a little bit slower than the other, so we can interfere if something happens. Here in the next slide, I would like to show you how we observe the inscription process. So what you see on the left side is the inscription captured by the camera, and you really see how every line is inscribed line by line, and the white light there is actually the red light, which is scattering now in the new FBG. And we calculated the FBG at 5090 nanometer, and you really see in the video how the grating at 5090 nanometer is slowly growing. Yeah, after we built several sensors, we tested them in our laboratory, and some of the results I would like to present to you here. You see the spectrum on the left side before and after the inscription, and you can clearly see at 1565 nanometer a sharp peak, which indicates a successful inscription. On the right side is 200 times magnification of our sensor. You clearly see the capillary, and inside the single mode fiber, here the single mode and the capillary is fused together, and the red light, which is scattered at a point-by-point FBG, is clearly visible. We also tested our sensors in a pressure chamber, and as you see, there's a drift of the shift of the FPI spectrum, like it should be. We had the same resolution before and after the inscription, but more important in the spectrum is that the FBG is stable, and this is because the temperature in the pressure chamber was stable. So this indicates a successful inscription. We tested our FBGs also in a controlled Cooper block, which we built especially for optical fiber sensors, and applied temperature, and you really see the temperature drift, the temperature shift of the FBG. But more important for biomedical application is the stability. So we tested our sensors in a burette of water to simulate the behavior in a bladder of a patient, and we saw that our sensors were before and after the inscription still stable over 30 minutes. So we had a good stability after the inscription. We also tested the sensors on an automated underwater vehicle. Here on the top in the picture, we placed them on the right and on the left side of an aluminum cross and tested them in a water tank, and saw a very good correlation with their reference sensors. Yeah, and with this I would like to sum up my presentation. I showed you several solutions we found, for example, the different techniques, the point-by-point technique and the sawtooth technique. And we tested the sensors before and after the inscription, and so we had still a very stable sensor with a good pressure measurement and a high correlation to the reference sensor. So at the end, we can say we successfully inscribed FBGs into FPI sensors, and we found new methods to inscribe FBGs into fibers. And for the future, we hope to test our sensors in vivo in cardiovascular measurements, and it would be nice to integrate this process in a commercial optical fiber pressure sensor production line. Yeah, this project was supported by the Sounds Foundation Ireland, by the Irish Research Council and the ECOST STSM, and we got many support from other departments. And if you're interested in this project, here's a QR code which leads you to the website with more information. And with this, I would like to thank you for your attention. And if you have any questions, I would like to answer them. The reason that we choose this one is that Professor Kalli was already working or did already many research in this field, and he had some very good success with this method. So we use this method he already proved to integrate it in our sensors. So it was already a successful research, and we combined both techniques. I'm not sure if we would expect problems, but what I can say is that for this particular wavelength, it took very long time to find all the parameters to inscribe into the core, especially in an FPI sensor. So to do the same for, let's say, 1.5 micrometer, there could be problems, but at this point, I'm not able to see this.
So good morning, everybody. Thanks, Mr. Chairman. I'm Murad Alexander Ben Abdallah, and I'm really happy to present to you part of my work on high-speed tunable FDML laser interface to continuous FPGA acquisition system for Fibre Bragg Grating accelerometer interrogation. So in this presentation, I'll begin with the context, an introduction, present the issues and the design and operation of the Fourier domain mode locking laser and the continuous data acquisition system, to present also the characterization results, and finally the conclusion and the perspectives. So in our optical measurement laboratory, it's a laboratory of the Atomic Energy Center in Paris, we do applied research. So we start from the needs of our customers to develop applications, softwares, hardwares, components. And today we can say that we completely control all the process, beginning from the inscription or drawing of Bragg grating which are spectral filters used as transducers, and also sensors in signal processing. And finally, we integrate all this in a system, an embedded system, to provide to our customers plug-and-play systems. So our customer needs are mainly materials and structure monitoring for intelligent manufacturing, smart structure, etc. In the 15 last years, we have developed many FBG systems, starting with the Cosmos here in 2000. It turns at a frequency of 50 Hertz with a spectral range of 30 nanometer and a resolution of 20 picometer, and it can address 8 channels at the same time. After that, we tried to improve one or more of these parameters to fit to our customers' needs. So that's why we developed also Bragg Fast, the Smith system, the Bragg Light system, the Bragg Fit system, and another version of Bragg Light. And this study is part of this logic, and that's why we've been interested in FDML laser systems to try to improve. Our goal was to improve all these parameters. So to have a better scanning frequency, a larger spectral range, a better resolution, and to try to be able to address the more Fibre Bragg Grating as possible. Now let's talk a little bit about the technology of FBG's optical fiber sensors. As you can see here on the screen, here is a fiber optic in which we have drawn 3 gratings with different periods. So the grating is a periodic change of the index of the core and works like an optical filter. So when we send an optical spectrum into the sensor, we find the same spectrum but without 3 specific wavelengths that are reflected by different grating. So when we put a strain on this sensor, we'll change locally the period of the grating and so change directly the Bragg wavelength. So we can say that the reflected Bragg wavelength change and varies with change in strain or in temperature. And this kind of sensors present many advantages like listed here and can be used in really many applications. For example, the oil and gas, aerospace, transport, and civil engineering. Now, our major issue in this work is to try to be able to detect slow phenomena, represented here with a candle, and also transient phenomena, represented with the explosion. To be able to do this, we need a laser source able to interrogate these sensors with a high frequency and at the same time have a wide spectral range to enable a large multiplexing. In this picture, you can see a schematic view of the tunable laser source. It's based mainly in an SOA, so semiconductor optical amplifier, a Fabry Perot, also a Fabry Perot, commanded and controlled by a function generator via an electronic command, 2 isolators, 1 coupler, and 10 km of fiber. Let's see how it works. So we begin with by sending a sine function to the Fabry Perot to control the move of the mirrors. After that, in another hand, the SOA deliver an optical spectrum which travel into the ring cavity to go to the Fabry Perot, and the Fabry Perot is a filter, so it will select for every position of the mirrors a specific wavelength. These wavelengths will travel into the ring cavity, and for example, for the green one, the green wavelength, when it comes again into the Fabry Perot, the mirror should be exactly at the position corresponding to this wavelength, otherwise it will be filtered. So to be able to laze, we should synchronize the cavity length with the scanning frequency of the mirrors. And for scanning frequency of about 20 kilohertz, we should have in a cavity length of about 10 kilometers. So as you can see in this graph, we have drawn the output spectrum of the laser for each one of these frequencies. So 20, 40, 60, 80, and 100 kilohertz. And what we can point out that the higher is the frequency and the tinier is the spectral range, and this is due to the Fabry Perot, the response of the Fabry Perot. So we spoke about the FDML laser, which is the first part of this work, and now I present the second part, which is the continuous data acquisition system. So it's composed by 3 photodetectors, an acquisition board with the 3 channels with 250 megasample per second digitalization. Also an FPGA card performs the continuous digital pretreating and process data stream at 1.5 gigabyte per second. The PC, also a PC to calculate the Bragg wavelength and to save data. All this should be synchronized by means of master clock with a function generator. The idea is to interrogate with our FDML laser a Bragg sensor line, which is the measurement line, and at the same time a spectral reference, which is here in our case a calibrated FP, Fabry Perot. The idea is to be able to calculate the Bragg wavelength by overlapping the Bragg sensor response into the response of the calibrated Fabry Perot. So to be able to say that our system works, we have tested it with the Fibre Bragg Grating based accelerometer, which have Bragg wavelength at about 1.55 micrometer. We passed it on a vibrating port, and we sent via system a request of 800 hertz of frequency and an acceleration of 50 meter per second square. And the idea is to try to find if when we do the measurement with our system, if we can find the request that we send to the sensor. So the results are here, and you can see in red that the acceleration request, and in blue the measurement using the FDML laser system. And you can see that we fit pretty good the acceleration request. When we do a transformation, Fourier transformation to calculate the frequency of our blue signal, we find that the frequency is about 785 hertz, and this 1% of error is due to the sampling in this graph. So our accelerometer application doesn't go over 1 kilohertz of frequency. That's why we try to put another application which can goes up to 30 kilohertz of frequency vibration. And this is a video of the results. Here, what you can say here, this is the interface of the software we developed. All these are the parameters of pretreating. This graph is, let's start first of all the video. Okay, this graph represents the answer of the Fabry Perot, calibrated Fabry Perot. These are the response of the Fibre Bragg Grating. This is the evolution of the vibration in real time of the response of Bragg, the move of wavelength. And here is the evolution of the frequency of vibration of the Fibre Bragg Grating. Okay, I've finished. So, in conclusion, we can say that we have developed successfully a C-band tunable high-speed fiber source in FDML type. This system is self-referenced spectrally through a calibrated Fabry Perot, and the acquisition and signal procession are shared between an FPGA and a PC at 1.5 gigabyte per second. The measurement rates up to 100 kilohertz were obtained. An average speed measurement test achieved by interrogating an FBG-based accelerometer at 800 Hz, and another test even faster with a piezo-driven was also performed at 30 kilohertz. What remains to be treated is the linearization of the laser response, currently controlled by a sine function, to reduce also the oversampling, the integration of the system processing in a real-time OS, and the integration of the laser to be able to do a field demonstration. So thank you for your attention. The line width. Okay, the line width of the tunable laser is less than 1 picometer. Find it in the exact line width. I think it's around 0.2 picometer, but you can do the calculation to make it to hertz, and it defined specially by the finesse of the Fabry Perot.